Alright, so what we're looking at here is Unit 6, Lesson 10. And for this lesson, you're going to need to look at one of your reference tables. It is the table on vapor pressure. So what exactly is vapor pressure? Well, a vapor pressure is if you have, for example, a liquid in a container. That liquid is going to evaporate, meaning turn into a gas. And that gas, as it's rising up, creates what's called vapor pressure. And we're going to look at a couple of things. We're going to look at what causes the vapor pressure of a liquid to be strong or weak. It's based in part on the bonding, but there are other things that affect it, as like temperature. And then we're going to look at one of the reference tables. So, for example, if a liquid has a high vapor pressure, what does that exactly mean? Well, what it means is that it evaporates easily, which means it has weak intermolecular forces, and it's most likely nonpolar. Um, that's a pretty good example, and you'll see an example of each on one of the next slides. Okay, well, actually, here's an answer. Ethanol has a higher vapor pressure than H2O. I know when you think of something having a higher something like high vapor pressure, you think for some reason it's stronger, but it's the opposite because you have to think of vapor pressure as being how quickly or how easily something evaporates. If something evaporates very easily, that means it has very weak forces holding it together. That's why it evaporates easily. So if you compare ethanol, which is is an alcohol, to water, ethanol evaporates very easily. It has a high vapor pressure, and that's because alcohols in general, like ethanol, tend to be nonpolar, so they have weak intermolecular forces. Water, on the other hand, is a polar molecule. Remember, it's a dipole. Um, has stronger intermolecular forces, so it evaporates more slowly. And here's what we're talking about. One of the factors that affects vapor pressure is the strength of the intermolecular forces. So, and you should be writing this down. This is a water molecule, right? Notice if you do the lines of symmetry, if a molecule has one line of symmetry, it's polar. If it has more than one, it's nonpolar. And the only way to split this in half so you have the same thing on both sides is this one way here. That means that it is a polar molecule. Once you've determined it's polar, you then need to determine what end is going to develop a positive charge and the other one that's a negative. That's what's called a dipole. Oxygen has a higher electronegativity, so this end will be slightly negative, and this end of the molecule will develop a slight positive charge. This has strong intermolecular forces. Okay? If you look at the methane molecule and you do lines of symmetry, it has a bunch of different lines of symmetry. So it is nonpolar, and it's going to have weak intermolecular forces. So this will have low vapor pressure. This will have high vapor pressure. This is extremely important that you remember this. Okay, so that's one thing or one factor involved in the vapor pressure of a liquid. Second one is simply temperature. What can you do to a liquid to make it evaporate faster? Increase the temperature. So if you increase the temperature, you're increasing the vapor pressure. As you can see from the diagram here, this is at 80, this is at 90 Celsius. This will have higher vapor pressure. Look at the number, and it's obviously not going to be this simple, but there's more molecules of gas moving up that creates more pressure, and that's vapor pressure. And okay, so let's look at Table H in your reference tables. Table H in your reference tables is a graph. It's vapor pressure on the y-axis in kPa's. The bottom is temperature. You can't see temperature, but that's what it is in degrees Celsius. And you'll notice there's a dashed line. That dashed line, and you should write this down, and let me get the pen color here. The dashed line that you see here is telling you this is normal. That is normal or standard air pressure. And you'll see where that comes into play in the later on. If you look at this, where these intersect, where these points are called the normal boiling points, because that's what the boiling point would be at normal air pressure. So that is the normal boiling point for propanone, the normal boiling point for ethanol, and of course the normal boiling point for water is 100. That's the temperature it normally boils at. And you'll see ethanoic acid. Notice that they have a very different normal boiling point. The boiling point for propanone is 55 degrees. For ethanol is approximately, we'll say 79. It's a little bit less. We know water is 100. And we know ethanoic acid is about 5, 10, 15, let's say 117. What accounts for the differences in the boiling points? And it's all based on intermolecular forces. These have weak intermolecular forces. This has strong intermolecular forces. That's one of the things that you should understand about this, is that the lower the boiling point a liquid has, that means the weaker the intermolecular forces. The higher the boiling point of a liquid, the stronger the intermolecular forces. Okay, so let's go through. We already did this. Highest vapor pressure evaporates easiest, weakest intermolecular forces. And one of the things you have to be able to do is a couple of things. If they give you in a question the vapor pressure and they ask you for the temperature, you just follow the graph. If you give you vapor pressure, you look for the number on the y-axis, you follow it over until you hit the line for the substance they're asking about, and then drop down to the temperature. They could also give you the temperature and ask you for the vapor pressure. And you'll see this on the next slide. Right? Right? So this is basically what we were just talking about here. Sometimes I get ahead of myself, as you can see. All right, so let's take a look at the question. Now, if you can't follow along on this chart, try and follow along on your own reference tables. All right, so let's take a look. It says, what is the vapor pressure of propanone at 35 degrees? So they're giving you a temperature, and they're asking you for the vapor pressure. So this is the y-axis. This is the x-axis. So let's locate 35 degrees. This is 30. This is 35. Follow it up until you hit the line for propanone, and it is right here. So the pressure at 35 degrees for propanone is going to be about 48 kPa's. As you can see, that looks about right, right? If you move over, it's going to be about here. Oops. All right. That's a fairly simple question. Number 2 says, what temperature does water boil at if the pressure is 70? Well, remember how we said that if the air pressure is normal pressure, you would look on this dashed line until you hit the point that you're giving. But now they're saying, well, what if the pressure is not at 101? What if it's only 70? So let's find out what this would be. That'd be 55, 60, that'd be 60, 70. So 70, you follow it over until you hit the line for water, right? 70, 70. Here's the line for water. At 70, you drop that down, and that would be 75. That would be 80, 85, 90. So water would boil if the air pressure was 70 kPa. Water would boil at, of course, 90 degrees Celsius. Now, number 3, we talked about the normal boiling point of a liquid, and that is simply the boiling point when the line where the two lines meet, where the dashed line meets the line for the substance. So ethanoic acid, we said that its normal boiling point would be this here. You drop down here, and it's going to be about 117 degrees Celsius. And those are really just the 3 main questions that they give you: the normal boiling point, the boiling point at a different pressure, and then what would the vapor pressure be at a specific temperature. And that is, I believe, it for vapor pressure. Let's just move on to this. Okay, let's look at one of the phase that we've talked about a couple of times, about sublimation, and then we're going to move on to the next lesson. Sublimation is when a substance goes directly from the solid to the gas phase, skipping the liquid phase completely. And that happens generally if the material, the solid, has very weak intermolecular forces. Example of that would be dry ice, would be solid carbon dioxide. It goes directly to carbon dioxide gas. There is no liquid phase involved in that. Another example of that would be iodine. Solid iodine would be another example of something that undergoes sublimation. Alright, let's go through check for understanding. How could you change the boiling point temperature of a substance without adding anything to the substance? The only way to change the temperature that a substance boils at is to change the air pressure, which means you would have to change the altitude. You either go higher up in the atmosphere or lower in the atmosphere. So if you went to the top of a mountain, air pressure is lower, which would mean that the liquid would boil at a lower temperature. You spill a glass of water on the floor. How could you get the water to evaporate faster without using a mop or something to soak it up? Well, you could increase the temperature of the room. So you turn the heat up. The hotter the temperature, the faster something's going to evaporate. Or you could take the water and spread it over a larger surface area. That would also make it evaporate faster. Okay, so let's look at the difference between evaporation and boiling. They are the same phase change. They're both going from a liquid to a gas. One's occurring at room temperature, and the other one is occurring at a much higher temperature. So what affects how fast something evaporates? Well, we already know it's intermolecular forces, the temperature, and the surface area. Boiling is when the vapor pressure of the liquid equals the air pressure pushing down. Normal boiling point is the temperature that a liquid boils at standard pressure. And just to save time, I'm not going to go to this video here. And that's normal pressure. That value is listed on your reference tables. Okay, and again, I'm just to save some time because the video is already too long. We're going to end this